Right. Good morning, people. Let's go ahead and finish my riddle and remember, it all deals with psychology and things like that. Tell you the screenshot, things like that. I'm telling you what to do. Now, let's go ahead and, if you see where I'm highlighting here, I want to show you the. Hopefully, you'll see the overlay, the lines, how parallel they are with the scaffolding. Scaffolding's approximately 6 feet apart. These uprights, and they're pretty plumb. Tells us that the base here is pretty level from here to there. These are non-adjustable wheels, so it's parallel. Now let's go ahead and look at this image again. This time, let's go ahead and bring up some colors. And I'll tell you where I'm going with this. This is the pure cap, as I said before. Now, the pure cap, let's do the saturation of the colors first. Alright, so I'm getting rid of the shadows in there. I'll zoom in. Okay. So now as you look at the material there, you see that it doesn't have the that color. We got rid of the color issue. We got rid of that dark color. You see back here, this is a rope that they used for a safety line, so you don't fall down in there. Just to guide you, not to fall down. It's not actually, that's not actually the intent, because it doesn't work that way. It's just to tell you, hey, you're approaching the edge. Let's go ahead and come out of this one. Okay. Now let's look what I directed your attention to in this image. A couple of places, a couple of videos ago. Directed your attention at the top. So right here is where I directed your attention, and this is where I did this. I was trying to show you an elevation change, right? An elevation change. This would be the pad. Let's go ahead and I want you to visualize the pad here. Now extend it on top of this pure cap. Alright, extend it on top of the pure cap. Let me go somewhere else with it a little bit. Let me just jump to that. I was going to play around a bit, but I won't play around anymore. This is why you don't see steel. Go backwards one. This is why you don't see steel. Okay, this is why you don't see steel here at these locations. Why you don't see any steel here, any pull out or anything else. Is it almost like it was formed in the dirt there, but this bump out right there. I'm gonna get rid of it so you can look at it. You can pause and shoot it. Nevertheless, it's pretty damn good. Pretty good. This is nice and plumb, so they used plywood. This wasn't just dirt formed. This appears to be pretty level across the top of this pure cap. Pretty flat. How about that? Pretty flat. And the pad went on top of there. I want you to think about the critical shear zone that it created automatically by default, because the pad's on top of here. This creates that, instead of a small column like we have at the deck, where you have this small column area, this amounts to a large column. Let's change colors on that. This amounts to a large column distributing load across as I Columbo moves you 1, 2, 3. Well, 3 is set up like this. If you guys remember some video ago, the 3 is more like this. The 3 setup of the pure caps. It's like that. Does this one look like that, or does it look rectangular? So this one appears to be the cap for at least 4. 1, 2, 3, 4. So the configuration would be a 4. So it would look, could be 4, right? And then there we go. I'm sorry. That's 4. And then there's our pier cap in the background here, our pier, our column. So it's your column right there. But the what you notice is, again, no reinforcement here. It didn't pop off. It didn't break. There's none over there. It didn't happen. This is on top of this. Now let me show you. Before I get to that, let's data stack this line here. This is your construction joint where they butted one connection, concrete, to another. And then they might have dowed it. They might have let the reinforcement just run wild and bulkheaded it. Let the concrete come here, remove that bulkhead, and then pour it to this face. But that is a indicator that this is where a slab was one where a pour stopped, if you will. That's right there. I'm going to show it to you in a second again. I'm going to show it to you in a second, in a moment. Not continuous. Confirmation, rope, right? Rope would do this. It does not look like rope, but we're going to confirm that it's not rope. Okay, so ladies and gentlemen, let's now, again, we owe a shout out to the engineer from Florida over here that sent us that. Remaining anonymous, does not want to be harassed. Let's look at the image here. Again, this is the top surface. This is the top surface of the pier. In other words, even though visually this looks like it would butt there, it does not. It goes across the top of this and marries over to here, both sides. Across. Doing so, just so you guys know, you create a tributary area between the two of them. This tributary area being smaller here than from, say, this edge to way out here somewhere. This is a larger tributary area. This would be more stable. We can't look at that now. We don't have an option to. Let's get rid of that. Moving over to your left of the... Okay, let me pause. Okay, moving to the left of the image. These are tire tracks from the forklift. They're right up there upon that line, the construction joint I just mentioned, headed towards that wall. Headed towards that wall. Tire tracks. The tire tracks apparently rotate. Looks like something like that, maybe. Maybe they go all the way over because of the visual of that, but nevertheless, the secondary track, can't see it over here. Is there internal? Is there external? So it would be like that, or they would be like this, right? So somewhere about here. This matters. I talked about the crack here, right? So there's no cracks here, what I'm looking for. Now let's go over the cracks, this one that I revealed to you. And you know, when I do a Columbo move, I say, look at that. I'm trying to bring your attention to it and want you to find more. Well, we also have, and I point it down here, I want you to take note that this is an elevation change. Remember, I talked to you about shadows and all that, but this is a step down. Step down. These are two different elevations. This is a pad here and a pad there. This is pad 1. This would be pad 2, the lower one. So this is pad 1. This is pad 2. Pad 1, pad 2. Now let's prove it to you. the shadow. See the shadow, non-continuous? It's right there, the elevation change of it. And that shows you this pad down below has stopped there, and there's a fracture here behind this cone. It continues over, perhaps. So we have a pad that's tilting. That is, this whole pad out here is kind of dangerous. It's fractured here. As you map this, here's a load that we can talk about there, the vehicle loading. And then we follow this fracture here. Look at this fracture. And let's map this one back over here. We know this one. So it looks like this might be it right here also. So let's go ahead and tie those in. All right, so we got a pad that's rotating down. This pad, this pad right here. And we're going to call it a separate pad based on this crack right here. And we've got a rotation, a cantilever that's more like, so if I could triangulate, I would do something like this. I'm not sure if this is connected back here or not. So I'm not sure if this section is still holding this pad up. Or the reinforcement. Reinforcement, question mark. So let's go back over to there and let's look at it. There's the tracks again. So here's our tracks, car tracks. Here's a fracture. Not sure what this is, that a drain or not. Not sure, not sure, not sure. Okay. This is, not sure. Unknown to me. Unknown. But I want you to see the shadow. Let's go back to the shadow again. The shadow is right there, right? That shadow tells us that this deck is rotating. Now, let's also work out other things. There's some steel here they use, reinforcement, with this rope. And I ran out of rope there and just laid it down. There's a shadow of the rope. To stop you from walking over to there, but it's dangerous to walk here also. It also doesn't have fall protection on it. So this tells you it's probably greater than about, someone's head falling on it. Just data you just stack up. With that said, this one appears to be sticking out of the ground and needs these caps like this over this one. That one's pretty damn dangerous, impaling hazard. Here's our loose steel, or debris, if you will, or the discarded. They're not using it. And they just went over there and grabbed it and repurposed it, it looks like. I'm guessing it came from there. Repurposed it down here. I don't know what the courts would think about that, because now you can't, it's not tagged. It's not tagged, and you don't know where it came from. And that's what I want you to notice about the pile. Not tagged. So no tags. How are you supposed to be able to keep track of this evidence? How are you supposed to keep track of the evidence untagged? Okay, so now you guys will see the pad was really I really wanted you guys to dive in when I pointed down there to see the shadow. I said there's a crack down here. I talked about that crack. I wanted you guys to see the shadow and figure out the elevation changes. When I circled that one, I wanted you guys to see it. And then there's your crack. So this pad is rotating down, hinge point back here. Doing pretty good, isn't it? Now, this would be an open crack up top. The hinge right here, open because of the rotation. And the force multipliers down the bottom as it's now can't rotate. This pad here will be pad number 2. So pad 2 is stable. So as this tries to rotate down, it's pulling across the reinforcement that goes across the top. All right. This will be continuous down here. So let's put the yellow reinforcement going across. So that's trying to open, right? Right there, open. And that would be here. At the bottom, it's under compression. It's getting real taut. tight. But that creates that prying action and putting even more tension on this one, trying to hold to support it. It gets bound at some point, meaning it can't rotate anymore. It's not free to rotate because it's bound over here. Rotation on this side, this would be pad 2, or is this 1? This is 2. Well, it's 2 now. So then we'll call 2 over here. And we'll call this pad 1 again up here. This is pad 1. So here's pad 1 and 2. As 2 tries to rotate, it runs into just a few inches down here. So 1 is stable. 2 is rotated down. See that? Take note of that, what that would look like underneath. If you could walk under here, walk under and visually see, you would see this. You would see 1. This is 1 again. 1 is up here, right? That's 1. You would see 1 pretty stable, and you would see 2. Well, I don't think 1 has that much deflection based on the openings here, and this is all part of 1. So you would see 2 rotate it down like that. Rotate it. And that gives you this lip. As you would look here, up top, you would see the lip that looks like that. Right here, eyeballs. Well, that's not really good eyeballs, is it? I'm sorry, I'm a little new to doing eyeballs. Kind of like the one I started there. Let's see. Nah, I'm getting there. Okay. So then you would see that the eyeballs. There, you would see that difference. And that gives you a rotation back here. Again, a lot of tension in here somewhere, holding this pad from rotating down and flipping over, because it also has 2 directional rotation. As you can see, that's open. All right, let me go from here. Okay, very noteworthy is that you do not see the concrete that was removed from this section. I do not see it stockpiled anywhere. How did they remove it and where did it go? I don't see a ladder that someone climbed down here and left there. You know, they just, maybe they didn't leave it. I don't see where they stepped here and used that as a dirt ladder. I see this stockpile material here, like I said, but maybe the excavator came over here to dig this hole, so it was over here at one point, an excavator. And as they were digging, it caused this fracture, overloading the pad. So as they're doing their exploration, they're diving into this. They're also doing damage. So they're damaging the structure permanently, not non-destructive, but destructive. This is very destructive, this investigation. It's not non-destructive, it is destructive. And a lot of it is giving corrupt information, such as this. You know, this is corrupt. This can be used as data to talk about it, and like I'm doing with you now. But if it uses data to say about how that this fracture existed and this pad, you know, was failing, no, they created this failure. They created this failure. There is evidence of the of equipment that's over here. Yes, it's on the outside of where the fracture should be. I need this to be pressure loaded here. This does not indicate it. This is why I talked about that. Pointed this here. For probably if people would know, I was hoping to leave this alone in the comments. Hopefully you would have said it. But let me just go ahead and say it. This means this is a rubber tire loader here. Or it is what? So you know the way I do it, guys. You know the way I talk. Is this I'm devious with the way I want you to catch on. I want you to challenge me. I just gave you a clue. I said rubber tire loader. Remember, I always say trust, but verify. I said rubber tire. Here's the key there. Tire. Now I want somebody to call me out on this. To call me out on this. And for you, you know, I'll give you another clue. Hold on. So here, okay. Here is the rubber tire loader. Oh, I'm sorry, that's an excavator right here. That's the excavator. There's the rubber tire loader. Those are the tires. Look at the footprint. Look at that footprint. Okay. Now, which one? So which footprint is this one? Which one is it? Is this the rubber tire loader or is it the track loader? Which one is it? Now keep in mind, we only see one track here visible to us in this imagery. We don't see the parallel track or tire. Which one is it? The track loader has to spin like a tank, whereas the excavator, the forklift one can turn like the two tires are parallel in the back, and the two in the front can turn like a car. So here are your holes again, right? You figured out what they might be now? I think there's another one over here. Oops, nope. Your holes, core samples. And now, what do we have here? What do we have there, right? Isn't it beautiful how it maps through? What appears to map through? Isn't it very interesting? I want to bring you to this one. Keep in mind, look at that line. Continuous path of that line. Isn't it interesting? I'm showing you, bring your attention to the elevation change also. That they're not of the same elevation. There is a bump, right? Using the shadow, the depth that's created. It's not like this, and it's not like this. It's clearly pronounced in this area here. Then we have, where's the other one? A lot of excavator scars on there. See the scar? That's these scratch marks. A lot of excavator scars. So not to confuse you, again, we do not see any reinforcement inside here. I made it very clear in the previous video, and I'll make it clear in this one. Is that you would see cut-wise where the reinforcement was, high, low. Where the reinforcement was offset a little bit, high, low. Offset a bit. What presents there. So we don't see any of that reinforcement inside here. We don't see any rebar, save one piece. It's kind of weird. Might have been the it might have been the securement for the forms. I think this piece here might have been something still left behind after the forms to tie the one side of the formwork over to this side of the formwork. I have a different image, a better image of this, and it appears to be rebar. But one piece down low could have been used again as a reinforcement, rather, to secure the outer forms. The two sides, shore work would have been used also, possibly more than likely, since these two were being poured, that they use each one to shore the other one up. And then the outer section was shored on that side. So if it shifted that way, it was supported. And the same for the back side on this side. This side would have been supported, braced. So it looks something like this. So here is a pier cap. And then put some bracing between it. Whaling. And then pier cap again. And then bracing. And bracing, some strong backs across here. And then concrete goes in. And here are your pier caps. Your piers. And of course this is more than that. And what else we have here? So it's going to be a little larger. Okay, so maybe I'm looking at that one piece that's right here. It's part of some support system that went across. And then we have that little detail to account for there that looks like some bad shoring or something right here. It's on this piece right here. Right here. That shoring is kind of different. It's maybe the excavator did it. Maybe these are excavator marks that somehow was able to rip into this. Interesting, they didn't bother coring. They cored the floor, but they didn't bother coring this. Nor do I see where they cored the floor and overshot into their core sample into here. So seeing some partial holes, perhaps not, but perhaps not. But coring, not seen here. So these have not been tested. But the subsidence, I want you guys to think of, when you go to the Broadwalk, you see piers there. So find in this location where piers have subsided. And piers for your boardwalk. The wave and it was collapsing, and they had to redo the pier, this boardwalk, and they had to raise it up because it didn't go down. The surface tension, skin friction didn't work out. Find where they have some other indicators of subsidence. Not just isolate this building, because clearly there's two buildings. Well, the one to the left, I think it has one of the deepest footers around, the new building. But the other one to the right, find out why isn't it having subject to subsidence. They use this approved method. And the footprint is lighter too, if you think about that too. But so you'd have to find something similar. Just look for any other proof of subsidence there. Remember, FIU University's got a lot of skin in the game. They want to prove that. Now again, they're totally discredited, because remember they had the FIU bridge collapse, and did you see their head engineering department come forward and say, "Oh yeah, we think we know what it is. It's subsidence. It's this or that." Well, that's amazing, because they did not. And FIU is now wants to get involved with that lady that wants to be their professional witness now, gatherer, the head professor, the subsidence. It's just so much skin in the game for them to just do this. But they're not speaking up about their bridge collapse that killed 8 people. It killed 8 people. And they're mute on that. They have mute. They're nothing. They're mutes. All right. So here's another image showing you the pad elevation change. Now, this one being down, this side, let's call this is pad 2 again. This is elevated pad 1, let's call it. Pad 2 being lower than 1 visually. We would look for cracks here to see if there's a rotation, the same as I pointed to you before. So I look into this field here and look for cracks, a rotation. And it was a hell of a rotation, wouldn't it be? I mean, it's so consistent. It would have to be, you know, amazing, right? And you'd also have to have pad 2 firmly sitting on top of something that was not. So let me take some liberty here. So this is the underside of pad 2. The one that's right up here, this is pad 2. I know what I'm doing here, right? So let's do that. It's the underside of pad 2. And it happens to be filled with solid fill material. But right on the other side of pad 2, just by chance, pad 1, now let's do pad 1. Pad 1 happens to suffer from subsidence, right? There's the soil consolidation, and there's a gap here created here. Let's change colors. A gap created here from the soil not being compacted, or water, you know, consolidation, shrinkage, going into the soil, expanding it, shrinking, expanding, shrinking it, drying. And I don't mean shrinking the soil as in making it smaller like a human or whatever, you know. I mean shrinkage as in consolidation. And then we would see over here to see if this is also true. Then this edge, a new elevation change also. You can't get this changing, dropping pad 1 going down, without also having this edge going down. So I don't see that. This just looks like fit and finish. At the bulkhead, they ran up there, and maybe they started from this end putting the concrete in. By the time they got down there, they were like, we're coming up a yard short. And the guy was like, make it work. And then they started doing what they can to make it work. And this is the best they can do to make it work. Quote, make it work. Now, with that said, that looks like a nice elevation change. Make it work usually doesn't look like that, just so you know. But this does look like this is much tighter here. And as I progress down, and again, you know, buildings and things like that were dropped on this pad. I can't imagine that they drove across this every day, lip-wise parking, lip, boom, 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 and nobody said a word about it. I don't see that. I don't see that happening here. I don't see it. I don't think that's true. I think it's part of construction issues, but it exposed our construction joint. And I think the joint looked like this one. Very, very nice. Very sharp, very clean. But the end result was that one after the demo guys got in there. Perhaps we get better imagery. They can give us more clarity to that. Now, I really looked on this wall for a construction joint, and I couldn't find it. I searched, right? I searched for a joint on this wall system. On each one of the images sent to me, looking at the top, when I talked about that long wall where we looked at it from top view, we looked down it, and we saw, that's when I was talking about the bulkhead. You know, we looked down it, and I could not find a construction joint anywhere. This wall, how did they deal with expansion on this wall? This wall, 150 feet long. Apparently it dealt with it. There's no bulging of the wall. There's no spalling of the wall in certain places, apparently. It's just something in my mind. And that would be, here's another image sent to me, identifying the camera and the wall system. And no expansion joints that I could find. None. I've gone around this structure. So ending the video with, which one is this? The track loader or the tire loader? Track excavator or the tire loader? Look at this. So is that a tire radius or is that a track radius? Can you guys tell me? Yeah, I'll give you this one. How I do my mapping of cracks. So that would be a rotation. And that would be, this is the anchor point. Okay, anchor point from there. So they're consistent. These two tie together. I would make them. This is not moving. Ooh. Okay. All right. So here is our. This would be our critical shear zone here. All right. So this in this crack system, because it cracks up to here. All right, as it presents, as I can see it now. Another image might give me better data. So this tells me that this is more rigid, right? This is rigid on this side, and this would be more of a tributary area. This tells me that it's rigid on this side, right? So I put it as a critical shear zone over here. The thing is, though, and this is based on loading, on the loading, however this was loaded, from the building falling on it or the excavator. Before they cut this open, were these cracks present? If so, that means that here's our critical shear zones, right? And the next one might be back here. And when the structure collapsed on it, let's say, when the structure collapsed on this, it hit this zone in here, the tributary zone, and caused these fractures, perhaps not by an excavator at all, but by doing collapse. So you got to just think of all the options there. But nevertheless, we still have it. We still got this rotation. It happens to be right where they cut it open. They didn't go any further. It's interesting because it all has to come out. This all has to come out. Why are they limiting themselves? Are they really worried about the flooding? It's going to have to be worked with anyway. It's going to be dealt with. They're dealing with it now. They're pumping this. Are they really worried about that? Now they're not going to close this up. What's their intention here? It's just to do inspections. You're going to check elevations, but this is already... You can't check it right here. You're going to check it off what? Another one? Are they going to compare left and right? These two are going to be the comparisons and not the one out here? Not the one where maybe a building didn't collapse on it? The one with the least amount of collapse forces on it would be the one. It would have tension forces on the one by the. So let's do that. So here's the. Let's just do this. Let me do the building like this for a second. I'm doing it rectangle. I know it's different shape, but let's divide it. Let's divide it here. This is the main collapse over here, right? This one back here, the columns back here, as the building rotated over, they were in tension. So how much did they release? The least amount of damage are back here. The couple of columns back here that just bent over a little bit, but just a little bit before they released. So these columns would have the pier caps. You can probably take a better measurement off of. The pool decks. The pool decks where they punch through. They're awesome for taking elevations off of, but they're not. They're like this. The pool deck. So I believe they're like this. But you can get your elevation change. You can get your elevation and check that for your subsidence. Remember, subsidence is their reasoning. We have a start point of the pool deck or parking garage area. I said or parking garage area, always leaving open a percentage of position change. But the pool deck and parking garage area definitely is our starting point. So they seem more critical to be inspecting those for subsidence than over here at the structure, the main structure where they collapsed the structure on it, imploded a structure on it. Now let me show you how you can get failure via subsidence. I talked about this before, but let's just use a column. Let me just put a column here, and I'm gonna tie it together with this pure cap and pierce. All right. So this is below surface. All of this. It's this guy. Is this guy. Okay. And it's tied in with steel to the piers system they used. And I think this is a four system here. 1, 2, 3, 4. So even though I'm showing 3 here, there's another one in the background here, 4. So you get some soil receding, whatever you get a void down below. I don't care how you get there through global warming, right? It warmed up and somehow it shrank down here where this should be 50 tons each. So these are significantly deep, and times 4, and they're stating that at that zone where it's so much, where it can take 50 tons of force, 50 tons each. So combined, 1, 2, 3, 4, 200 tons. 200 tons, and this one takes 200 tons. They're side by side. They're pressure loading each other's zones, if you will. This one going here, they're loading each other. They're making this soil down here even tighter. That is, if you put this one in, you'll probably get the 200 tons sooner. So they might not be at the same elevation. It might this one to the right. Let's say that one to the right might have gotten there. You know, considering that they're pressure zoning each other. So this one might have gotten there. You know, this might got there at 30 feet. This one might have gotten there at 27 feet. So they might be offset height-wise, the base differently, but they just cared about this force. Okay, so 200 tons, let's call it. And 200 tons each, 200 tons. So 400 tons between two of these little ladies. So somehow the subsidence is able to undermine these guys, undermine them, and cause them to change elevation. So here they're at elevation of concrete deck, which is right here. So the concrete deck is right here. All right, so I'm going down on that one, but it still shares the load down onto it. Okay, so it's right here. And the subsidence, which is down here, takes place. It somehow magically gets on these piers, and it shrinks back. Wait a minute! It doesn't just these things have surface tension to them also, so it erodes that surface tension, and it erodes the surface tension on the wall of this one, because this is even up here. Soil's up here, right? Let's change the colors. Soil's up here also, all around this big giant ass pure cap. So it erodes that also. Oh, wait a minute, but underneath of here, it's also like a giant plate, a giant foot. Oh, it erodes that too. All right, so you need all of this to lose its ability to support, and then you get your elevated drop, your elevation change. Upon getting an elevation change, this is just theoretical for you guys. I don't mean this. So upon your elevation change, this droppage. Oh, great. So I can do it real fast. No, I can't. Hold on. So what I did here is I took some liberty here and I put this back end up here. This one a little higher for us. But I want you to see the layout here, so I'll change the colors and I'll change it back. Just want to show you where I am. So this is the pure cap, right? Pure cap. That big chunk of concrete. I mean, literally, that's the pure cap right here. And these red marks here are the 4. I'm going to go with 4 piers down to 50 tons each. I think they changed it though. I think maybe it's 50 tons each, and then they just added more to get your higher values. And then this yellow here is the represents the soil that they drove it into. As you can see, it's underneath of here also. Underneath, it's everywhere, right? It's everywhere here, including underneath of here. It's this entire surface. Entire surface on its underside is supported is on sand. Sand, even the sidewalls. So all of the sidewalls, all of it counts. Surface tension. So to get this to drop down, so they need this to drop, this subsidence, you need this whole system, this entire system to lower. Because we don't see it fractured. There's no fractures here to showing it took tension and broke free. We don't see it fractured here where it broke free, or on this one, or in any of them that I looked at. We don't see it broke free, and I'll explain that in a minute. That is that, so I'll do that now, the deck. So let me do the, yeah, so I'll do the deck like this. So here's the deck. Okay. And then here are the tie-ins, the rabbit ears. Okay, now let's say the deck was rigid. So the deck is acting as a strong back, a piece of steel. Let's just theorize that the deck could do that it's so rigid. It's so strong, right? That when this pure cap, all these down below. So let's get you, oh, great. One more time. Okay, let's start again. So when the pure cap, so I just changed colors. So when this subsidence settles down, this concrete doesn't settle down with it, let's say. Let's say it's so strong that it's anchored at the wall and anchored at another column. And then let's just pick on one pier. You only need one of these piers to subside to start this ball rolling, incidentally. So, I gave it some serious thought. So it's, so I'm not just trolling here. So I'm just saying it didn't happen. So this one elevates, there's no evidence shows it happened. This one changes direction because all this soil down here on one of them has a direct tap to the river, to the ocean, and it's just going in and out, in and out, in and out. And over 40 years, it creates a void. And finally, this just drops down 3 inches. 3 inches. All of it just drops down 3 inches. But wait a minute. It drops down like an elevator? Or would just like any foundation that fails in a house, you always get a corner that drops down, a rotation takes place. Well, we don't have any rotation taking place. We keep finding this whole deck is flat out here. Everywhere we look, it's pretty flat. No rotation, no leaning columns, no rotated columns. Because that one rotating creates a rotation on your column also. On your column head, on this one. And that would then rotate in this deck. This pier head would rotate, causing an uplift here, let's say rotating in this direction. And a down rotation here, causing a fracture, if you could theorize that. Okay, that's one version of it. Now let's do the version where it just settles down magically all by itself. It just settles down. It just goes straight down the entire pier cap. Everything, the whole system, the column, everything. Well, now it's just pulling down and it creates a sag right at the column head, which would then change this and it fractures all of this zone times 2, each side of it, because it's equal. And that would cause your butterfly. Problem is there's no column at the butterfly that would have initiated this here. So there's nothing there in the middle. It's a clear shot where cars are. So it doesn't account for the butterfly area. You'd have to start that somewhere else. We've got no cracks that indicate that on top. There's no cracks that they're indicating like that at the columns. It's always outside in the critical shear zones that we find the fracture starting. That is by the planter box. So this theory gets shit canned. Although I worked it, right? So it gets no go. It doesn't happen. It doesn't happen. Subsidence would look like that and behave like that, and it doesn't happen. There's no rotation there. There's no breaking here because it settled down 3 inches. It didn't settle down 3 inches. They're looking for it, but it just looks like no, that these things are behaved and performed as they did, as they should have. Again, you can check the elevations. You can look for, buckling here if you can find one. But buckling, one doesn't mean a thing if it's still flat up here. There are no fractures. So now I got one more scenario that would do that. Let's say the deck is so strong. I gave this hint a long time ago at the pool hot tub area. At the hot tub, there is a hot tub. So I'll give you at the hot tub, there's a base. And at that base, there is a fracture. It looks like that. This fracture is very interesting. But the hot tub didn't move. But at the hot tub, that fracture is friggin' huge to me to resolve. I need to know how it became about, because that is a tension fracture, meaning that one side's pulling from the other, and that would be, if anything, a subsidence over there. The problem is, it looks like they put their base for the hot tub on top of the pad, so that fracture could just simply be the pad and the pull deck trying to do the same action I showed over here. This fracture there, it's there. You can find it, and you guys want to hunt it. And when you find it, you'll say, but that would put it starting over there, literally at the hot tub here, meaning it. But that fracture is so tight. I mean, yes, I found it, but it's like, you know, 1/8 of an inch. It's not much. It's there though. Nevertheless, it's there. It's not a compressive fracture. It's a tension fracture, meaning it's tension. It was created via tension. And that's very interesting, yet it should have been a compressive one. There's no rotation seen there. But it also could be when the pull deck collapsed, that it impacted the surface below. And the fracture I'm looking at was post-collapse fracture. I couldn't tell that it was painted, but now the paint's, you know, been knocked off and things like that. So I can't tell if that fracture is. Let me see if I can find an image. If not, I'm ending the video. So let me just use this image to, since this is the one they destroyed, NIST destroyed 2930. They just fractured it all to hell down there. So using this image here, this is all gone, and this they use this in the 3D. You see it laid out like that with 29 written on it. It's all fractured to hell. Anyway, let's use this one and talk about subsidence to help you understand it. So if this was anchored across the deck, strong back, these if it could hold it. Remember, to hold it, it's only got 4 rabbit ears up here that interlocks this column with this deck. So I'm asking this part of the deck to behave, and it's only got 9.5 total inches of concrete. The anchoring part would be the top part. Let's do this. So here's the pad, right? And there's the anchor. As this pulls up, what's stopping it? Not this part. Some of it's intentional across the bond surface there. But it's this part here that's interacting. All right. So it's not much. We know that to be low there. So it's only a couple of inches. So what's stronger? The steel coming out of the floor here? The anchorage out of the floor here? Or this part up top as your subsidence happens. So now let's add a force, a directional force, subsidence. This pier cap is a pier cap under here. Let's just do that for liberty. Taking her liberty is going down. There's the yellow's going down. It's being subsided down, pulled down. As it pulls down, it fractures the deck, theoretically fractures the deck, pulling the deck down, and then it starts your butterfly failure. Or that implies that these are strong enough to be able to do that. First off, we don't have this. We only have some clown show who wants to talk about global warming, and FIU is one of them. I tell you that FIU's got some nice acronym for me. That all of a sudden can do this. Just it comes in from the ocean and works its way over, comes in from wherever the source is, and just starts creating 40-year havoc on here. And if that's the case, the $1 billion should be given back. So this is not in anyone's favor, that the owner's favor, to wish for subsidence, because if it's determined by the federal government that it's subsidence, then all the money should be given back. This was an act of nature, and money should be handed back. They didn't talk about GB back then. GB is global, GW rather. Yeah, I made my own initial, didn't I? GW. Yeah, George Washington. They didn't talk about George Washington back then. 1980s. So, like that. A little bit of California smog. That's about it, right? So there's what their claim is. Now over at the pool, they got the huge blocks there that hold the hot tub up. Rather, the one there is a fracture in it. Like I said, this could have been an impact on the base that could have caused that fracture here. And there's some steel in here. In terms of paint, if paint was inside of it, they painted it and paint was inside there. That was pre-collapse. This fracture shows with no paint inside the crack. That's post-collapse. It would like to see that. And it was painted, so it would be one or the other. Just like this. If I were to fracture this now, pulling this apart, I would see inside the fracture, I wouldn't see paint. Because there's no dry paint inside the fracture. But if it was fractured and then I painted it, you would see the paint down inside the fracture. So that's why this matters with that hot tub. So what we have here is the critical shear zone, right? And then outside the critical shear zone, we have this rotation. And we have a fracture back there that's existing. We've got right here, which I haven't revealed yet, a rotation there. There's a column holding up this planer box. But there is indication that this deck was doing this over here. That it was doing that over there. It's right there. I'm ending the video. That's my teaser. Love you guys. Bye.